just a note on that. So I sent through a few examples of questions. They might have adapted them, I don't know. I sent through a few examples from last summer's exam. So they will be based on things that might appear on the exam, okay? Okay, today is the final lecture of new material. Is there a yay? Yay. You guys have made it to the end. Well done. I don't know if I should be more impressed that you made it to the end or that I made it to the end. Like, I can't. Back in the UK, like in my old university, we had 10-week semesters. So by like week 8, I'm flagging. So I'm sure you guys feel the same. Okay. So I'm just going to go through a quick summary of both Wednesday's pre-lecture and today's pre-lecture, just because I wasn't here on Wednesday. So I won't dwell too much on these, but just give a bit of a summary. Obviously, if you have any questions, do please put up your hand or shout out. That's fine. So Wednesday's pre-lecture went through a couple more definitions related to trophic level and trophic status. This idea of unique predator dominant species, where if a species, for example, in this food web down here, if a species just has out degree 1, that means it's only fed on by one thing. Then we refer to the thing that feeds on it as a unique predator dominant species. We also talked about this idea of trophic status dominant species, where we count up the number of non-primary producers. So typically your primary producer is going to be plants. You count up your non-primary producers. In this case, there were 12 in this particular food web. And then we look for all the species that have trophic status greater than 12, and we class those as being trophic status dominant species. This tells us something a little bit about their relationship with other species in the food web and how connected they are, as well as how high up in the food web they are. Competition graphs. This is not a major component, but is something that you guys should know how to do. On the left-hand side here, we have a food web, which you've met multiple times. We can turn some of this information into something called a competition graph if we draw a link between any two species that share a food source. Okay, so here, the only two species that share a food source are sea urchins and small fishes. So on the right-hand side in this competition graph, we draw an edge between these two nodes here, indicating that there is competition for food. Okay, so how do we do this? We just look for any species that have out degree 2 or more, like kelp is the only one here. And then we draw a link between the things that feed on that species, okay? So it's competition graphs. Then went on to compartment models or compartmental models, depending on how you want to pronounce it. These are used for things like pharmacokinetics. So that's like movement of drugs within the body. We've also met them before in our aging models or models where we are moving cars from one location to another. And we're going to be talking about those in the context of Markov chains today. The key thing really is in relation to graphs here is that we can translate the information that we would encode in, say, a Leslie matrix into a directed graph. Okay, so the pre-lecture went through how to do that. So you should be able to go back and forth between these two things. Okay. That was the pre-lecture for Wednesday. And then today's pre-lecture. Actually, before I move on, does anyone have any questions from the first pre-lecture? No. Okay. The second pre-lecture for today, we're going to be talking about Markov chains and the page ranking algorithm, which is used in early search engines. So we have our compartment models, and we can draw a digraph, like on the right-hand side here. And if we now, rather than just having rates of going between one state and another, if we meet a certain set of criteria and think of these now as, say, probabilities of moving from one state to another, these probabilities have to sum to 1. And this gives us a few nice properties. And it means that we can construct things called Markov chains. So Markov chains are a particular type of model. They're used extensively in biology. The key things is that we need to, first of all, have a finite number of states. This will always be satisfied for you here. Okay, so we can't have an infinite number of different states that we can be in. When I'm talking about states here, this could be, say, juvenile, adult. These are different states, or it might be susceptible, infected, recovered, and so on. A model that is split into different compartments, and you can only be in one of those compartments at a time. We are measuring time in discrete jumps, so we don't have our continuous time models like ordinary differential equations. Here we're having discrete time jumps. And we're also transferring from one state to another with a fixed probability here. So this probability doesn't change over time. It's crucial. So there was this example here with population movement. So if individuals either have to be in the city or in the suburbs, we think about who moves from the city to the suburbs and suburbs to the city, and hence who stays in the city and hence who stays in the suburbs. We can come up with a digraph that describes this, and we know that we can move back and forth between digraphs over here, and then a matrix representation of that movement. Then if we want to work out, given an initial probability distribution, so for example, here we have a vector describing the initial probability distribution. This is saying that 85% of the initial population is in the city, 15% in the suburbs. What happens in the long term, or after any number of years or days, however we're measuring time? Well, we just take our initial population vector, our population distribution here, V0, and we multiply it by our transition matrix. And this is exactly what we did earlier in the course with things like the juvenile adult models, okay? So to work out what we have in the next time step, we take our transition matrix, times it by our probability distribution. And if you want to work out what's going on in the long term, you multiply this however many times. And if you want to think about the super long term as n goes to infinity, then we're going to be thinking about eigenvectors and eigenvalues. Okay. So in this case here, we can think about the probability distribution after a certain number of years. And in this case, it's 60% in the sub-city, 40% in the suburbs. Okay, so a key definition here is a probability vector. A probability vector is a vector whose entries are non-negative and sum to 1. Okay, this is kind of similar to what we looked at earlier in the semester when we would have, we were rescaling eigenvectors so that the sum of the entries was 1. And we can rescale any vector we want to have sum of entries equal to 1. If you add up all the entries in a vector and divide by that sum, then all of those entries will then sum to be equal to 1. So how do we understand the long-term behavior in these Markov chains? Well, they have this nice property because we have these probabilities here summing to 1. That means that we're neither losing or gaining individuals in these populations. Okay, they're just moving from one state to another state. That means that we always end up with our dominant eigenvalue being equal to 1. So you remember in these systems, when we looked at population models, we talked about, is the population growing or shrinking or staying the same size? If the dominant eigenvalue is greater than 1 in these systems, the population would grow. If it was less than 1, it would shrink. And if it's equal to 1, it would stay the same size. Here, they're staying the same size because they're just switching between states. We're not creating or losing individuals, okay? They're just moving, in this case, from one place to another. So what does this all mean? Well, we can write down an eigenvector, just like we would have written down an eigenvector earlier this semester. But we can also rescale this, either to think about a ratio, or we can rescale it in terms of the sum of those elements. So we add up the two elements in this eigenvector, divide by that sum, and that gives us an eigenvector that has the sum of its elements equal to 1. We refer to this as being a fixed probability vector. Okay, so that's telling us ultimately what are going to be the distribution of individuals, or whatever we happen to be modeling here. What's the distribution across the different states in the long term? Okay, remember, eigenvectors tell you about long-term behavior. Okay, the last piece of new material in this course is talking about the PageRank algorithm. Okay, and how we can essentially use these ideas of digraphs and Markov chains to understand the importance of web pages. And they do this by, and this is how the very first search engines worked, by essentially distributing the importance across all pages that you link to. Okay, so if a page has 3 links, we say, okay, we're going to equally distribute importance to those 3 pages. So each page gets an importance factor of 1/3. If it was 2 links out, then it goes to 1/2. If it's 1, it's 1, and so on. Okay. Doing that essentially means that we can treat this as a Markov chain, because these columns in this matrix will always sum to 1. And we end up with an eigenvalue equal to 1. We can then look at the eigenvector associated with that matrix, and we can rescale it then we can rank these pages according to this fixed probability vector, okay? So it's basically the same idea as when we have Markov chains, but it allows us to say which of these are the most important web pages based on how they're distributing importance through this graph, okay? So that's essentially how Google worked in the very early days. Okay, we're going to go through some problems now. Does anyone have any questions before we do so? No. Okay. Incidentally, next week, I will be going through a review on Monday of weeks 1 to 7, if I remember rightly, and then weeks 8 to 12, I guess, after that on Wednesday. So those sessions will probably give some hints as to the kinds of things you might be expected to do on the final. I'll repeat some of this next week anyway. Things that you've already been examined on are less likely to appear on the final. It doesn't mean that they won't appear on the final, but for example, you've not been examined on nonlinear systems or food webs or counting yet. So those things might appear on the final. You have been examined on linear systems. So linear systems might not appear on the final, okay? Or at least linear systems of ODEs. That gives you a few hints as the kinds of things that might and might not appear, okay? Okay, let's think about Markov chains. So first of all, I'm going to get you guys to do this first part. I want you to sketch the digraph, so the directed graph of this transition matrix here. And I'm going to give you the eigenvector as well. It's the eigenvector that is dominant, the one that is associated with lambda is equal to 1. If you plug this into a computer, you might get something like, let's say, 4/9, 8/3, and 1. Okay, so what I want you to do is sketch the digraph first of all from this matrix, and then think about this dominant eigenvector here, and then from there work out the fixed probability vector, okay? Okay, let's see what this looks like. Okay, so a digraph here. The first thing we want to do is we want to label these vertices here. You can call them whatever you like. I'm just going to call them V1, V2, V3. You don't need to have these arrows on here. You should label your vertices, give them some label. So let's do something like this. V1, V2, V3. I'd advise either choosing going down a column or going across the rows, okay? The reason being that you're less likely to make a mistake. So I'm going to go down the column. So this column here represents everything that's leaving V1, okay? So the first entry is just V1 to V1, which has weight 1/4. The second entry is V1 going to V2. Oh, okay. Should be a V2. So V1 to V2 is going to have weight 1/2. So that's this second entry here. And then V1 to V3 is the third entry with weight 1/4. Second column is going to be everything that's going from V2. So V2 to V1, there's nothing going in that direction. So there's no arrow like this. We do have V2 to V2 with weight 2/3. That's this entry here. And then V2 to V3 has weight 1/3. That's that entry there. And then one more column. We have V3 to V1, this entry here, with weight 1/3. We have V3 to V2. So that's going in this direction like this, weight 2/3. And then there's nothing from V3 to itself. Weight of 0 means there is no edge. Okay, have a show of hands who managed to get the correct digraph. Fantastic, well done. Okay, how about the second part? So here we've got a dominant eigenvector. So remember, this is the eigenvector that corresponds to the eigenvalue lambda 1 is equal to 1. We want to turn this into a fixed probability vector. So the first thing we need to do is we need to sum up the elements in U1. So this sum is going to equal 4/9 plus 8/3 plus 1, which is 4/9 plus 24/9 plus 9/9, which is 37/9. This is called normalization, what we're doing here. And then we're going to turn this into a new fixed probability vector by dividing by that sum. So we're doing 1 over the sum of U1, which is going to be 9/37 times by 4/9, 8/3, and 1, which ends up being 4/37, 24/37, and 9/37. Or if you plug these into a calculator, 0.11, 0.65, and 0.24 roughly. So what does that actually mean? Well, that means that in the long term, whatever this happens to represent, we would so let's write this out. In the long term, we would expect roughly 11% of the population to be in state V1. 65% in V2, and 24% in V3. So all I'm doing there is I'm taking the entries from my fixed probability vector, this thing on the right-hand side, times them by the 100, and you'll get the percentages correspond to it, okay? And note these percentages add up to 100. Show of hands who managed to get those? A bit more mixed. Okay, let's go on to slightly more concrete example. We can come up with a very simple weather model by thinking about the probability of it being, say, sunny today and sunny tomorrow, or cloudy today, cloudy tomorrow, cloudy today, rainy tomorrow, and so on. All of these different combinations using a Markov chain, okay? So here we've got a digraph representing these transitions. On the previous example, I wanted you guys to go from a matrix to a digraph. Now I want you in the first part here to go from a digraph to a matrix. Have a go at doing that part first, okay? And see how you get on. Okay, so we're going to do the same process, but in reverse. So I'm now going to think of that first column. So this is everything going out of the sunny state into sunny, into cloudy, and into rainy. Okay, so that means I'm first of all going to look at what's going from sunny to sunny. Well, the probability is 2/3. Sunny to cloudy is going to be 1/3. And there's nothing from sunny to rainy. So this is 0. Note, quick check to make sure that, well, it doesn't guarantee that your transition matrix is correct, but check that these columns always sum to 1. If they don't sum to 1, you've definitely made a mistake. Okay, let's go from cloudy to sunny. So that has probability 1/2. Cloudy to cloudy, no probability of it being cloudy in 2 days in running. This might not be a very good model for Vancouver. And cloudy to rainy, probability 1/2. And then the final one, for rainy, we've got rainy to sunny is 1/3, rainy to cloudy is 1/3, and rainy to rainy is 1/3. So all of these on this side are 1/3. Okay, so that's our transition matrix, which I've just called P here. The second part, we're told, suppose day 0 is a sunny day. Predict the probability of sunny, cloudy, rainy on day 4. Okay, so what does this mean? Well, our initial probability distribution is it's sunny on day 1. So we have a 1 for sunny here, 0 and 0, okay? So it's definitely sunny, it's not cloudy or rainy on day 0. And then if I want to work out if that's day 0, day 4 is going to be V4, which is just our transition matrix to the power of 4 times by V0. Now, the powers here, whenever we take a power to a matrix, this does seem to be a problem for lots of students. All this is saying here is we're doing P times by P times by P times by P times by V naught. Okay. This is matrix multiplication. What I'm not doing is if this is my matrix, I'm just going to make it simpler here, A, B, C, D, if it was a 2 by 2. What I'm not doing is I'm not doing A to the power of 4, B to the power of 4, C to the power of 4, D to the power of 4. Okay. When we have this notation here of P to the power of 4, it's matrix multiplication, P times by P times by P times by P. It's not the elements within P taken to the power of 4. Okay, that will give you a different thing. Okay, all it is repeated matrix multiplication. This is a laborious thing. I would not suggest actually working this thing out for yourself. If you did, though, you'd end up with something that's roughly 0.56, 0.25, and 0.19. So this is saying the probability of it being sunny on day 4, given that it was sunny on day 0, is 56%. Okay, or it's a 0.56 probability here. Probability of it being cloudy is 25%. Probability of it being rainy on day 4 is 19%. So if you start with a different distribution, you might get a different figures. Okay. The final part here, find the proportion of sunny, cloudy, and rainy days in the long term. So this is just like we had previously. Not many of you guys seem to get it. So have a go at transforming this into a fixed probability vector to work out the proportion of sunny, cloudy, and rainy days in the long term. Okay, have a go at doing that. Incidentally, if this was in an exam, I'm going to give you that eigenvector. I'm not going to expect you to, well, as long as it was bigger than a 2 by 2, I'm not going to expect you to calculate any eigenvectors bigger than a 2 by 2, okay? Okay, I'm judging by the chat, you guys have finished. So if you work out the sum of these elements, so the sum is going to be 3 plus 4 thirds plus 1. Should be 16 over 3. Then you divide by that to get your fixed probability vector. You should end up with roughly 0.56, 0.25, 0.19, which is very similar to what we had. So you see that even after 4 days in this system, we settled down into this long-term pattern really quickly. Okay? That won't always be true, but in this case, it happened to be true. The long-term distribution was predicted pretty nicely after just 4 days. Okay, let's think about another application of these things. So because Markov chains are inherently probabilistic, we often think about them in terms of games of chance. So in this particular gambling game, the probability of winning $1 is going to be 0.58. Probability of losing $1 is 0.42. And this is regardless of whatever you have at the moment. So this doesn't matter whether you currently have $1 or you have $4 or whatever. This probability is the same. And remember, we need to have this probability being fixed. It doesn't actually need to be fixed between these different levels. But the point is, if you currently have $1 now, your probability of gaining $1 is always going to be 0.58. If you what you wouldn't want is to have your probability of getting $1 today being 0.58 and tomorrow it would be 0.56 or 0.2 or whatever it happens to be, okay? So this probability has to be the same. And then here it happens to also be the same between these different levels. Okay, so they have to either have $1 or $5 to continue playing, and the game ends when they have $0 or $6. And they bet $1 in each round, and $1 if they win, and lose the bet if they lose, okay? So here, we're going to describe this using a digraph and a transition matrix, and then compute some probabilities of winning or losing based on your initial starting value, okay? So this is a digraph that's representing what's going on here. These probabilities here for 0 and $6 have to be 1, because if you start with 0, you don't have any money to bet with. If you get $6, you win the game and splurge that massive spending. Well, you'll have a big spending spree on $6, I guess. We're told that you always have a probability of losing $1 with probability 0.42, so there's a 42% chance of losing $1 regardless of where you start. Correspondingly, there must be a 58% chance of winning $1 wherever you start. So everything that starts in 0 stays in 0, so you have a 1 in the first entry. The second column, we have a 42% chance of moving left, so we have a 0.42 here. Nothing stays in 1. So remember, everything that is in this main diagonal down here that I'm highlighting in pink is things that stay in that class. Okay, so nothing stays within its own class except for state 0 and state 6. We can move left. So moving left is going to be everything just above this main diagonal with chance 42%. So everything above that pink line is going to be 0.42, except for this final entry on the bottom right here, because if we go into 6, we can't leave 6. Okay, so all these entries that are highlighted in green here, that's going from 1 to 0, or 2 to 1, or 3 to 2, 4 to 3, or 5 to 4. So moving left, we're losing $1. Every time we win, it's going to be moving to the right. So that's going to be everything just below this main diagonal here. We also have the same chance here of 0.58. Okay, and note, I'll highlight this in, say, orange. So this is the probability of moving right. And then in all of these columns here, note that the sum of these things is always equal to 1. Okay, this is what we need in for our Markov chains, right? Because we're not gaining or losing individuals or states or money or whatever we happen to be modeling. We're always moving from one state to another state. So we can't have these things not summing to 1, okay? Okay, that was an absolute train wreck. Okay, let's think about part B. So part B, if the gambler initially has $1, compute the probability of winning or losing in the end. Okay, so here, if we actually work out the eigenvalues of this matrix, essentially our problem here is that our eigenvalue lambda is equal to 1. We end up with 2 eigenvectors associated with this. So we actually have a U1, which looks like this, 1, 0, 0, 0, 0, 0, 0. I got the right number of zeros there, yeah. And another one, I call U2, which is the opposite. And this is because we have these absorbing states at 0 and 6 here. So we have these 2 eigenvectors. What we want to think about is what happens, rather than looking at these eigenvectors, we want to think about what happens if we start with a certain number of dollars here. So for example, if we start with $1, we're going to have an initial probability vector that looks like this. It's going to be my V0. And we want to know what happens in the long term. So long term, we can look at eigenvectors. We also know that our eigenvectors are just telling us something about the distribution in the long term. And we could just get this by brute force. So say what happens after 50 goes? What's our probability of being in a different state? So we take our V50, say, I've chosen 50 just an arbitrary thing here. We're just choosing a large number. And you could plug this into a computer, right? So you take this matrix to the power of 50, and you times it by your initial distribution. It could be to the power of 100, could be whatever, some reasonably large number. You do this, and you end up getting something like this. It's 0.678, I think. All these zeros down here, and 0.322. So within a large enough value of n here, so after a large enough number of tries, we basically have roughly a 68% chance of losing our money if we start with $1. And we only have a 32% chance of winning if we start with $1. We can do the same thing if we start with $5. So our initial population vector, our initial probability distribution is going to be zeros all the way down here. 0, 1, 2, 3, 4, 5. Yep, okay. So we do the same thing here. I'm running out of space a little bit here. We can work out what is a large number, say V50 again, by taking this transition matrix to a large power, timesing it by our initial probability distribution. Zoom in, so a bit more space. In this case here, if we start with $5, you should end up with a chance of losing something like 6%, and your chance of winning is 94%. Okay. So despite me screwing up the matrix horrendously, the point of this is to illustrate that we can use these Markov chains to get an idea about in games of chance, where it doesn't matter where you were 2 steps ago, all it matters is where you are now. That's a key to a Markov chain. We can make predictions about what is the probability of winning in the long term or the short term. And this kind of thing will affect when a casino, how they construct their games of chance, essentially, okay? There's one more question on here about PageRank. It's essentially the same as what we've been doing here in terms of putting transition matrices into digraphs and back and forth. The key thing here is about splitting up the weights accordingly, okay? Guys, just hold on just a minute, okay? We've only got a couple of minutes left. Previously, in all of the examples for the compartment models, you were given the weights on each of these arrows. In an example like this, you have to add the weights yourself. And the key thing with the PageRank algorithm is you're distributing the weights equally among all of the outgoing arrows from a vertex, okay? And these all have to sum to be equal to 1. Okay, so for example here, for vertex A, it has 2 arrows going out, 1 to D and 1 to B. So these both have weights of half. B, it has arrows going out to A and C, so these have weights of half. C only has 1 arrow going out, so all of its importance goes from C to B, so it has weight 1. And then D has 3 arrows going out, so they all have weight 1/3, okay? So if you're given an example like this, you would have to construct the weights on this digraph based on this idea of sharing out importance equally, okay? So you can have a go at this one in your own time. Obviously, I'll upload the solution. A final thing to just mention here is that several websites figured out how to trick these PageRank algorithms by noticing that they won't link to pages that don't link to them. In doing so, you can essentially game the system and increase your search result, okay? That is it for today and all the material in this course. I'll see you next week for review sessions.